Hello, everyone. My name is Carissa de Santos, and I'm going to be talking today about my project for this neural network and deep learning class. So for this project, I chose to focus on the equatorial Pacific and patterns in sea surface temperature in the equatorial Pacific. I myself am an oceanographer. I do small scale work, but understanding large scale patterns in variables like sea surface temperature, sea surface salinity, and other variables that are monitored by satellites and things like that is often something that's sought out in the field of oceanography, especially being able to predict patterns. There are oscillatory patterns that happen on scales of seasons to several years to several decades. So the implementation of different convolutional neural network models is something that's strongly emerging in the field, and I wanted to see if this was something that I would be able to do for the purpose of this class. So yeah, here is my website. Like I said, I'm focusing on the equatorial Pacific, applying a predictive model for sea surface temperature specifically. And we're going to be talking a little bit about the project, introduction, some background on ENSO, how I access the data, how you can access the data as well, how it's pre-processed, the model that I'm using, and then finally how it performed, as well as some things that it tells us about ENSO. So first and foremost to the project introduction. Um, like I mentioned, in the field of oceanography, being able to predict short and long-term patterns on global and regional scales is something that is very much of interest. And one paper that actually inspired this project itself was a 2023 paper by Sheng et al., which is called a modified U-Net model for predicting the sea surface salinity over the Western Pacific Ocean. And this paper was something that I found while trying to implement a U model in my own research in um, the domain of Baltimore, which I work in. So what they basically did is they utilized a U-Net model, which is known for some things that I'll talk about a little bit later in this presentation, um, to predict 6 months of sea surface temperature data in advance to try to understand some of these spatial patterns and also just test model performance for um, predictions using a small amount of input data over such a large scale region. So to kind of provide some background onto ENSO and why I would want to understand sea surface temperature patterns in the beginning, I'm sure many of you have heard of the phenomenon known as El Nino or El Nino Southern Oscillation, which is what ENSO stands for. So under standard conditions, we have easterly winds, meaning winds that blow from the east to the west that blow over the equatorial Pacific. And as these winds blow that way, they transfer colder waters off the Eastern Pacific Ocean Basin across the basin. So they um, make the surface waters across the equator colder than they would normally be, as well as some upwelling that happens along the equator. During the El Nino phase of this oscillatory pattern, these trade winds kind of relax a little bit, and because of that, the surface waters are warmer than normal in the equatorial Pacific. And this means that the temperature gradient from the equator to the poles is strengthened because we have warmer waters in the equator and it's still cold up there. Um, and because of this, there are some jet streams that exist at altitude, such as the subtropical and the polar jet stream, that are strengthened. As a result, there's a lot of like dynamic conditions that aren't really worth getting into. But as we can see here during the El Nino phase, we have the polar jet stream up here. We have the strengthened subtropical jet stream that has also moved down a little bit. So because of this, we're seeing wetter conditions in the southern United States and along Mexico as well. And in the northern United States, we see usually drier conditions. So these are strong teleconnections that happen on these 2 to 7 year time scales. Um, and they influence weather patterns that we are more familiar with, things like droughts, if it's a very dry year, um, because of El Nino in the northern United States, in places like California where it may not rain as much. And it's an El Nino, we may see higher levels of precipitation that could, again, lead to different patterns and different problems because we're changing the climate of a specific area um, for conditions that it's not really accustomed to. And because of this, it's being able to predict El Nino especially as it changes in a changing climate, is something that is really of interest, not only as just like an interesting science question, but also to the health and welfare of the general public. So now some background on the actual unit architecture itself. Like I mentioned, it was used in that Zhang et al. Paper, and in general, UNet is something that's used for image segmentation. It's often used in the biomedical field. Um, but it can be useful for applications related to satellite images, segmenting satellite images for variables like sea surface temperature, sea surface height, sea surface salinity, um, because it can process large amounts of images very quickly, which is obviously we don't want things that are computationally expensive, especially when working with global data, it can be very difficult. So it's important in that aspect. It also has that downsampling and upsampling process. That's why it's called like the UNet, because it's shaped like a U. Um, and because of this, it's like preserving resolution so it can pick up finer scale features that other convolutional neural networks cannot or have a harder time doing with the same computational expense. So moving on to the actual data and the pre-processing steps that were taken for this project. So the data used, there are a million sea surface temperature, sea surface salinity data sets available. There's satellite data, there's model output from CESM or ERA5. Um, for the purpose of this study, I used the extended reconstructed sea surface temperature or ERS version 5 dataset on their website. So this is a dataset of reconstructed sea surface temperature, which means that it is a collection of observations usually made by Argo floats across the global ocean. Um, and the holes are filled using statistical methods. This was done by NOAA's PSL lab, which is right here in Boulder, Colorado. Um, and it represents monthly values across the globe from 1854 to October of 2025. That being said, the first step was to clean up the data a little bit. The metadata of that NOAA provides states that there are a lot of holes in the observational record prior to 1880. So because of this, all the data was removed prior to then because there's a lot more error in the kind of interpolation in between different observational records on the global scale. So those were just removed for the sake of preserving um like the accuracy of the data. And I also removed any data in 2025 because it was not a completed year yet and the record wasn't there. So um, I just removed it to have 12 months, the full 12 months from 1880 to 2024 for each year. And the mean, I also selected out the Nino 3.4 region. So the Nino 3.4 index is an index that represents the sea surface temperature anomaly. This is the normal way that we kind of define whether something is an El Nino or a La Nina year, or whether it's not either. So this region is actually really small. It's about from 5 north to 5 south in latitude and about 170 to 120 degrees west. So it's a very small region, probably like just around this box here. Along the equatorial Pacific. I chose to extend that a little bit more to include around -60 to 60 degrees latitude and that same the whole longitudinal extent of the Pacific Ocean. When we are pre-processing the data, especially for a unit model, we have to put it onto a 128 by 128 grid for interpolation to start off with. Well, it could be any grid that's a power of two, but I wanted to have a bigger extent so that when we were interpolating onto that grid, there wouldn't be crazy values since it's going to be originally like 20 by 20, like 20 degrees latitude in total. So I increased the extent of that a bit. And then after selecting this data, I set up some of the model settings to kind of make the rest of the code a lot cleaner. That's way if anyone else wants to implement their data for kind of the same purpose of predicting some n amount of lead times in the future. They could, here is where I put my Nino 3.4 extended region. So if someone concatenates a bunch of other data sets, selects out their region of interest, their time of interest, they can just start here, and change any other input or output or dimensional names that they can. Um, like I said, I then specified the interpolation dimensions for some of the architecture in the future. I specified the lead time and lag time, so that's how many time steps you want to predict in the future and how many time steps that you're using in the past to predict those future time steps. So I'm using 6 months of previous time steps to predict 6 months in the future. To predict a max of 6 times in the future. And then seeing how the error changes with each of those max lead times. I included the number of nodes per layer, which is I'm using 16 filters, and then the number of hidden layers, which I'm using 4. So 4 downsampling layers, 4 upsampling layers in this neural network model, in addition to other dropout and pooling layers. We use some normalization factors, as we've mentioned in the past. If you don't normalize some of your data, the training process is either not going to work or it's going to take forever. So we use that to define my model. I specified some of the percentage of training fractions, the batch size, the number of epochs, and then something that we didn't super discuss in this class, but I used callbacks. So because I'm working with kind of a larger data sets, I don't really want to train for those full 200 epochs, but um, if you use callbacks, you can stop the training process early if your model's not improving by a certain factor within a certain number of epochs. You can also have it adjust the learning rate if your model's not improving. So like here, if my model doesn't improve by this, if the loss isn't improved by this amount for 10 epochs, we're going to stop the training process. Um, Before it stops that, if the model doesn't improve by that same amount for 5 epochs, it'll reduce the learning rate by 0.2 with a minimum value of this value here. So they're all just kind of ways to make the model more dynamic and the training process more user-friendly so that you don't have to be as vigilant about watching it and making sure that it's actually worth your time to do the full 200 epochs. Yeah. So at this point, some other pre-processing steps that we did was I actually interpolated onto that 128 by 128 grid size. I removed any nans, fix any problems with encoding in the variables to start with. I know in other data sets I've worked with, just Earth system data, there's always problems with it. So I encoded the variable names to be a specific type. And then I also established which callbacks I would be using here. So like I said, we're reducing that learning rate. If it's not model's not improving, we're stopping early. And then we're also saving our weights for future reference if needed. And if anyone wants to use this code, run it for their own data, or they want to just try it for this data, all that information can be found here. Anyone can download it. It's just a zip file. So yeah. Now to the analysis portion, which just talks about the model architecture. Like I said, I was using a UNet model. So here we have our input file. It's that 128 by 128 interpolated data set, and then those 6 lead times. We have a convolution layer, pooling, convolution, pooling, convolution, pooling, convolution, pooling. And these are all done using a swish activation function, same in the upsampling process. And then the final output is using a ReLU activation function, again with those 16 filters, those 4 hidden layers, both in the downsampling and upsampling process. And the Keras custom UNet model that is like pre-built into the Keras package provides a lot more layers than what is shown here. There are actually 65 layers or some crazy number like that, a very large number of parameters. So there's definitely documentation if you want to look more into that. And then once the model was actually built for the compilation, we used mean squared error as the loss function, atom optimization, and then that dynamic learning rate that I mentioned beforehand. All right, and then finally the results and conclusions. So the results, first, I want to talk about the model performance in itself, showing the root mean squared error in space and time. So as we can see, at the start of the training process, the loss was around a value of 52, and by the end, it has been reduced to about 0.32, which is great. We see that the model's performing pretty well within a short amount of epochs. It only had to run for about 70, and I did several runs. Most of them only ran for about 50, but I also wanted to show the dynamic learning rate, which um didn't actually end up changing in the other ones because the model performed well within a short amount of epochs. So we can see that the learning rate changes that we also want to implement also worked here at around epoch 60. There's that sharp decrease. It decreased by a factor of 2. It was multiplied by 0.2 at this point, because prior to it, we can see that there was starting to be an increase in the loss again. So it adjusted for that. So it was good to see that the changes that we wanted to make to that dynamic learning rate were actually being implemented into the model. And then finally, going back to the initial objectives of the project, in addition to making a model that could predict had low error, had low loss, some lead times in the future, we also wanted to better understand the potential spatial patterns, sea surface temperature, and maybe see if that provided any insight about ENSO. So first and foremost, we can see that the model lead time error, the error increases with lead time, which is something that you expect to see. When we're predicting just 1 month in advance, we see an error of 0.5, versus 6 months in advance, we see 0.54. So there's still, it's about half a degree Celsius, which is not wonderful, but it is still relatively small for predicting half a year in advance, which is interesting to see at the least. And then another thing I wanted to focus on was just this final image here showing the spatial patterns in root mean squared error at the 6 different lead times that we tested. So again, as you can see, it's not really changing that significantly in the values itself, but one thing that I did want to highlight is the temperature. I mean, sorry, not the temperature, the spatial patterns. So El Nino was actually discovered because of Peruvian fishermen who were noticing different yields of fish over the years. And I bring that up because we see these higher errors along the coast, the eastern Pacific Basin along the coast of South America here. And that's because this is like highlighting one of the kind of the fundamental faults of this training process, and something that Zhang et al. Also talked about, is that it has quite a bit of trouble working with areas that are more temporally variable than what the input data is allowing for. So like if you feed in monthly data, there's no way that you're going to be able to predict patterns that occur on different scales than a month. If you have upwelling that's happening on over the course of a few days, that isn't persistent over that long period, there's obviously going to be greater variability that produces error here. So we're likely seeing some of that upwelling in these areas that is introducing error into our model as the lead times increase. And although it's not something that I tested, I think it would be interesting to see in the future how, as we increase the lead times, these spatial / temporal variations are going to be affected. So yeah, that is all I have to share. Like I said, all the data and code is accessible on this website if you want to try it out for yourself. The code is pretty adaptable. There may be some just like extra pre-processing steps if you have multiple input files that you want to use. But yeah, I'm happy to take any questions.